Okay, we are at our very last lesson for Newton's third law. Um, now, the reason why I put this off for so long is that we kind of want to build up to it. We've talked about it, but everything we've kind of learned kind of leads up to this. Um, as well as we have to kind of think about Newton's third law problems in a different way than with FBDs, which is really what we've been focusing on so much so far. Remember that Newton's first law is that an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted upon by some force, right? The law of inertia. It doesn't want to change its motion. Newton's second law is F net equals ma. That's the result of Newton's second law. A net force on a mass causes an acceleration. Newton's third law is the very famous every action there's an equal opposite reaction. That's Hamilton. Well, it's Newton, but it's in Hamilton. This is really confusing for some people because they're like, yeah, sure, I can understand that. But then when you try to apply it, you guys always answer these questions wrong. So we're going to really try and drill this in. Now, we call these equal opposite reactions action pairs or force pairs. If you have a question where they say, what is the action pair in this situation? They are the forces that are equal and opposite. So they are very often phrased like this, where it's force of 1 on 2 and force of 2 on 1. Again, if 1 is exerting a force on 2, 2 has to be exerting a force back. And again, the most important part about these two types of forces is they are always equal and in opposite directions. So just kind of thinking this through again, we've talked about this. In particular, we've talked about this with the normal force, but the reason why these things don't happen, why you don't float away and you don't sink to the chair and the chair is not sinking through you. It's because in order for these things to not happen, and again, they don't, is that if you are exerting a force on the chair, which is in this case your force of gravity on the chair exerts what force up on you? What would we call that force exerted up on you? Well, if you have the force of gravity down on the chair, the force upward would be the normal force because of you're on the surface. We need that reaction force. Otherwise, again, if you were just exerting a force on the chair and the chair didn't exert a force back, you would crush the chair and start sinking through it. This has to be true for anything to remain at rest, right? With me sitting right now, I'm not sinking through the earth. The net force on me has to be 0. So if I exert a force downward, there needs to be a force upward for me to remain at rest. Now, when we talk about the force of gravity and the normal force, you would not call those action or reaction pairs. We're going to kind of emphasize this a bit more in class, but you have to think a little bit differently here. When we talk about the normal force and gravity, those two forces are acting on me. Gravity acts on me, the normal force acts on me, versus the force of my butt on the ground versus and the force of the ground on my butt. Those don't both act on me. I am acting on the ground acts on me. It's a different way of thinking when you're talking about Newton's third law. In Newton's third law, you're looking at least two objects and the forces going on in between them. When we're dealing with Newton's second law, you're looking at one object and just the forces on it. So we're going to emphasize this a bit more in class, the kind of different ways of thinking here. So all I want you to do though is create a note card for Newton's third law. You can pause the video here and then copy it down. And then that's all we're going to do for Newton's third law with this ed puzzle. We're going to try and drill it home in class. So once you are done copying this, the ed puzzle is done.